Okay, so let me fix my little camera here. Welcome to class. We have one extra person today, so that's nice. Thank you, John.
You're welcome.
So I'm going to keep going where we left off from last time. But I just want to say I got most everybody's Hello World submission, and I left comments on Canvas for you. And so we have another project due this Saturday. It's the performance benchmarking. I've already seen some interesting results from Robbie. So that's pretty cool. So I want to continue where we left off with chapter 2, talking about the role of compilers. Kind of the things that, the major things that compilers are going to do for you. So inlining. If you don't, inlining is where the compiler, we saw this actually the last class period when I tried to profile my little toy code and the function disappeared. So basically what it does is it inserts a complete function into the place where it's called. This saves space on the stack, can allow useful optimizations like code folding. It prevents instruction jumping, which reduces register pressure. It helps the most with small functions that are called often. In C++, inlining is absolutely necessary for performance. Okay. You can add an inline keyword to your functions, but unfortunately the standard says this is only a suggestion. The compiler can do what it wants. Now every compiler actually has its own little directives that you can add to a function to say you must inline this, or you can think about inlining this, or don't inline this. That's also an option.
So,
Yes.
I don't quite understand why inlining is better.
Okay. So let me
I
explain.
understand what it's doing, I just don't understand why it's better. Does that make sense?
Okay. Then let me go a little bit more into depth on this. So I need more space here, but here's our function. Okay? Not our function, our program. Okay? And it's going through and reading, I should say, here's a function in your program. Okay? So the CPU is going along and doing stuff, okay, and it does some more stuff, and then it comes to a point where it has to go to the function. So what it's got to do is it's got to take this function, load it into memory, into the cache, run its instructions. No, don't do that. Run its instructions, and then jump back to where it came from, at which point it now has to find this in the RAM or on the hard drive, depending on how big your program is, load that back into cache, and keep going. Okay? So basically there's that stopping and starting that's going on there. It has to jump, and those jumps cost time.
Okay, so the compiler just loads.
It basically takes this and sticks it right there. Okay. Another thing it does is the stack. I haven't talked about the stack, but the stack is a special place in memory. Okay. I actually don't know where it resides. I'm guessing it resides on the CPU somewhere, but I could be wrong. But it's different from your RAM. So the stack, it's called a stack because they stack stuff. Okay.
Makes sense.
So say you have like a main function, okay, and in it you have like some integers, okay. When your program starts, it runs the main, and it's going to place function arguments and variables on the stack. And then let's say there's a function call in here somewhere, so it goes into the function and it has some arguments here, and it has, say, a double x, okay, and then it returns something, okay. So first off, the m gets placed on the stack, the x gets placed on the stack, the return value gets placed on the stack. Okay, and then when that function exits and goes back to main, then all of that stuff gets deleted. Okay, and we're back to where we were in main. And if you've ever heard of a stack overflow, what that means is you ran out of memory on the stack. And you don't usually see that because stacks are really large nowadays. But you can do it if you get into an infinite loop or a infinite recursive function, or fun stuff like that. I have done that. So, but by inlining it, it saves space on the stack, and it can allow useful optimizations such as constant folding. That's kind of the big one. So if you call this function like this, normally that 1.0 gets stuffed into a variable m. But if it inlines it, it knows, hey, m is 1. Now I can go through and do more optimizations inside of the function. Okay? And all of this is in an effort to reduce register pressure, speed up your code, and especially when you're working with C++, inlining is absolutely necessary. There's like a 10-fold difference from inlined to not inlined code. And I'm going to show you an example of that here in a bit. Unfortunately, the book mentions this can cause instruction bloat, which overwhelms the L1 instruction cache. I wouldn't worry about that. Okay, we're just not going to worry about that. If you want something to be inlined, though, it needs to be in a header file, or it needs to be in the same physical file. So you can have multiple functions in a single file. And so if you want it to be inlined, it needs to be in there somehow, either in the header file or in the C file. Does that make sense?
Where else would it be?
Well, it could be in a separate file. If it's in two separate files, it cannot inline it because it doesn't know it's there. It doesn't know what it looks like. Does that make sense? The compiler doesn't know. All it knows is, hey, there's this function, you're calling a function. Well, that's great. I don't know anything about this function. But if you put it in the same file, it can inline it. So if you want to prevent inlining, you can do that by putting them in two physically separate files and compiling each file individually. You compile this file into a .o, compile the other file into .o, and then you link the two together. However, nowadays, compilers are starting to get what they call link time optimizations, which can overcome that. And the GNU compilers don't do it very well. I've heard Intel's compiler does it very well, so which is not surprising. So, anyway, any questions on that? Okay. Now we need to talk about aliasing. Okay, so let's say we had a function, and I'm just going to type this out. I think it might be easier. So, yeah, I keep them for now. Okay, let's say we had some function here. I'm not going to do strict. I guess I should do strict C++, huh? Void my function make this a little bigger and we'll turn off the lights. And I forgot a B. There should be a B in here. Okay, and now we're going to do Oops, there's one more thing I forgot. Okay, so this is just our simple vector triad. So all the function knows is that it's receiving pointers. Okay, and in C and C++, those pointers are allowed to alias each other, which means they're allowed to point to the same location in memory. Okay, so if we called this function we'll just skip that part. We'll just say my function and we'll have some okay, so oh yeah.
An initial step.
Yeah. We'll assume everything's been done correctly. Okay. So basically, if you were to take all this, what we have now is AI equals AI plus AI times AI. Okay, because the pointers are allowed to alias each other. And the compiler has to throw in certain checks for that, which slows it down. Now, this doesn't seem too bad until we have something like this. Now we have something that looks like this. Okay, so what do we have here?
You want that B to be an A? Or no?
No, not right now.
Oh, okay.
Are you passing in 5 arguments to a 4-argument function?
No, it's 2.0.
Oh, that's a point. Okay.
Yeah, that's a point. Sorry, should I make it a teeny bit bigger there? What we have here, this is just a scaling function, right?
So you're saying there's something wrong with this?
Well, now what happens if we pass in this? If we pass in two A's, we're now doing AI equals S times AI, which is the scaling function that we did last time. These are technically not two separate pointers. They're not two separate blocks in memory. Okay, now what happens if we do... Okay, I know this is technically wrong, but it'll get the point across.
It's going to be really slow.
Why?
Because you're accessing it. It can't pipeline.
Right, because now we've introduced a dependency. But if you were to just look at the function by itself, you just look at the one function all by itself, the function itself doesn't know that. The function does not know that B is actually A minus 1. And so you're right, we've introduced this loop dependency into it, but the function doesn't know that. So when the compiler compiles the function, it has to throw in aliasing checks and make sure that the two are correct. Or sorry, that the two pointers are independent of each other. If they're not, it'll actually create like 3 different loops, and it'll choose at runtime which one to use depending on what's been sent to it. Or it slows it down. So this aliasing is just bad.
So, moral of the story is don't do that.
Basically. So in C, there is a keyword called restrict. Okay? What this restrict keyword does is say that there is no aliasing. And so that is an optimization that you can use in C. However, the restrict keyword does not work in C++. Yes?
When you do this in Fortran, does that mean every time you create a pointer that it checks every other pointer that's created to make sure that it's not aliasing?
No. In Fortran, no.
How does it guarantee that it's not aliasing?
It doesn't.
Okay.
It just assumes.
Oh.
Plus, there weren't pointers in Fortran until 2003.
Okay.
So, with those, there are restrictions on those as well. But they are allowed to alias in Fortran. So, it's up to the programmer in Fortran to make sure that there is no aliasing. Otherwise, you will get incorrect results. Especially when you're doing like a matrix transpose. An in-place transpose will do that. Anyway, so in C++ though, most compilers have you can do that in C++, and it has the same effect as the restrict keyword in C. Most compilers also have flags that you can give them that say function arguments do not alias each other. However, at that point, you've turned it into Fortran, where it's now your job to make sure that is true. Okay? So, in aliasing, I've seen some numbers. They typically say that it's like could be up to a 20% difference between assuming aliasing and assuming no aliasing. So, there's that. Go back to the PowerPoint here. Okay, like I said, in C++ you can use the __ restrict keyword. You can use compiler switches, F argument, no alias, and don't lie to the compiler. Okay, if you're going to use that switch, then make sure it's true. In Fortran, aliasing is forbidden, like we said, so you don't have to worry about it.
Wait, so that F argument no alias just means it's not checking for aliasing?
Yes.
Okay.
It's not going to run checks. It's going to assume that there is no aliasing.
The optimization just assumes that you can, so no aliasing.
Right, and so it won't build separate loops. It'll say, oh, these two things are different, so maybe I can throw everything in an SSE register now. Because if they're not different, then maybe it can't do that. Okay, so now I want to talk about C++ specifics. C++ has this wonderful thing called overloaded operators, and Fortran has them now too, so you can actually run into this problem there. So we have problems with temporaries. We have problems with dynamic memory management. Those are problems. However, lazy construction allows you to maybe speed things up, and the standard library iterators allow you to speed things up as well. So there's some pluses and minuses here. So I want to show you an example from the book that I put together this morning. Copy. Okay. So this is an example from the book that I actually wrote up here. So we're going to have a struct called point. It has 3 pieces to it, x, y, and z. Okay, so we declare a default constructor here. This is a second constructor that takes 3 values and plugs them into x, y, and z. We have the destructor. We have a copy constructor. Okay. We also have a move constructor if you're working with C++ 11. We have the copy assignment operator. We have the move assignment operator. Here we have an addition operator, so we're adding 2 points together, and that you'll see the return value on that is a point. And then we have a scaling operation where we multiply a point by just a double. Okay. So now we come to the actual program. We're going to create 2 points, A and B, have a third named C. And we have this very simple, innocent looking piece of code here, where we say C is equal to 3 times A plus 2 times B. Okay. So now if we compile this, and then we're going to run it, here is a list of everything the compiler has done. Can everyone see that okay? So, we constructed A and B. We constructed C, which had no values, so it used the default constructor. We used the triple constructor. We used the move. We moved it, we destroyed it, we constructed it, we moved it, we destroyed it, we constructed it, we moved it, we destroyed it, we moved it, we destroyed. And we output those, the values of C, and then we destroyed the 3 to close out the program.
I'm very confused.
I know. So, this should help make things a little more. I thought those were already uncommented, but they weren't. So, okay. So the very first thing it does, it goes into the scaling operation. So we had, oh, wow. Okay, that's really tiny. I typed that out wrong. Copy. Okay, so let's take a look at this side by side here. So you see the very first thing it does is the scaling operation. So it comes in here and it's scaling a point. And this point happens to be 3.0 times A. Okay, so it calls this operator and it constructs a new point, hence the triple constructor, with these values. It then returns that and moves it into the addition operator. Okay, after...
Where's move? What is move? Is that just equals? Oh, okay.
Move is here. Okay, it's called the move constructor. And I'm not going to talk too much about this.
Okay.
Maybe at the end of the class we can go more in depth about what it is, how it works.
Okay.
But the point is it moves it, and then it destroys the temporary value. Okay, then it calls the next scaling operation, 2 times B, and does the same thing. So we get scaling, we create a new point, we move it, and we destroy the temporary value. At that point, both values have been moved into this operator, this addition operator. Okay, where we default construct the temp, we assign everything, and then we move the temporary value into a temporary value, which is here. So basically it looks like this. We go C equals D plus E, C equals F, and then just C. So this is kind of what's going on. So 3 times A and 2 times B, those get moved into temporary variables, D and E. Okay. The addition operator gets moved into a temporary value F, and then the move assignment operator is invoked to assign everything to C. At which point, these 3 temporaries, 1, 2, and 3, are destroyed, and we're done. It's complicated. But my point here is that C++ involves a lot of temporaries. There's a lot of memory allocation, a lot of memory destruction. There's a lot of stuff going on. And they try and hide that from you.
So for every operation, it creates a temporary variable, basically.
Yeah. Basically. If you do it the naive way, which is this way. So, back to the PowerPoint here. Don't overload operators unless you know what you're doing, which is using what's known as expression templates. So I just want to show you something else real fast. If we change our flags a little bit, and we make that, and then we run that. Okay. So you'll see I've gotten rid of a lot of moves here, and by specifying a higher optimization, I also eliminated the flags that were preventing some optimizations. And we've now, instead of, we have far fewer moves. We do have still a triple constructor, a default constructor, and then the move assignment. And now I want to show you something that I thought was really interesting. I'm going to comment out these output statements. We'll make, and then we'll run that. And actually, I take that back. Never mind. Not interesting. All I did was take them out. My bad. I was looking at it wrong this morning. Anyway, so basically, we're still having to create these. We have to allocate memory. We have to construct them, which there's lots more stuff going on in there than we don't care about, until eventually we come to this move assignment. So there's still at least one move assignment, constructions and deconstructions of 3 temporary variables. And those can really eat into your time. They prevent loop optimizations. So those are things to be aware of.
So how do you get around that?
You use nice libraries, or you use what's called expression templates, which is very complicated and works really well, I should say. So, but that's a very complicated topic. Another way to avoid temporaries is to pass to functions by reference. Okay, by default, if you don't have that little ampersand sign, it will make a copy of your values. There is one exception to this, and that's primitive types. So primitive types are your integers, your doubles, your floats. Those are called primitive because they're built into the language. Primitive types typically can be optimized well, and if you pass, every time you pass something by reference, you're allowing for aliasing to happen. Okay, and so by passing by value, it knows that there's no aliasing and it can ignore optimizations. Or it can optimize, not the other way around. So primitive types you want to pass by value. Classes and things you want to pass by reference. Okay, so also C++ has a tendency to frequently allocate and deallocate memory. This is a slow process on both ends, so don't do it if you can't help it. If you allocate everything up front. However, there is also the option of lazy construction. So in C++, you can, right after here, we can make a new point. That point doesn't exist until we get to this place. So let's say here we have an if statement. If c.x is greater than 3, then we do something with point x here. Okay? My point being that this doesn't get allocated until we go into the if statement. And so if the if statement isn't done very often, then you can save on time and memory by only using that memory when you actually need it. And there's an example of that in the book. But, oops, wrong button. Also, you could try a static allocation. And static allocations are done at the beginning, at the startup of the program, and they're never touched again. So that's another option. All right, now we need to talk about standard vector. Who here loves standard vector? I do. No, you don't. Why?
I prefer using arrays.
But a standard vector knows how big it is.
Yeah, but it has an overhead on it.
Okay, and what is their claim about the overhead? C++ people?
I don't know.
Inlining!
Oh,
Inlining takes care of the overhead. Okay.
I doubt it.
So, when we're dealing with standard vectors. Okay, so we have a vector. I'm just ignoring standard, sorry. We want a vector of doubles, and we'll call this x, because I'm boring like that. And then we do x dot resize 100. Okay, now we have 100 doubles in our standard vector. And we want to loop through those. So we do okay, so that seems fairly straightforward. Standard vector was designed to have what they call the random access capability, which is done using the overloaded brackets operator. However, the book claims, now I should note this book was written in 2009, so 6 years ago. So this may have changed. I don't know. But the book claims that the compiler will refuse to optimize this. It'll refuse to use SSE registers and so on. So what you want to use instead is the iterators available. So that's one way to write the loop. You could also write it like this. Sorry, like this. And then you do, let's see here. Actually, let's change this name. This is the way the book lists it.
So the auto keyword just specifies that it's an iterator?
So, yeah, the auto keyword is to save on typing, but it's actually a part of C++ 11. What it does is it says the type of I it depends on the return type of x.begin.
Oh, okay.
Okay, so x.begin returns a const iterator
Okay.
over a standard vector. So this is one way to do it, and then this is another way to do it. And for a vector, not for any of the other container classes, but for a vector, the iterator is literally just a pointer. Okay, and compilers understand pointers. And so by doing it this way, you get the optimization that you want, or this way. And there's a new C++ 11 way to do things, and I'm not entirely certain of the syntax, but it's something like this. Although I can't say anything about the optimization properties of that.
And it's I equals 2, not if I equals 2?
Right, because it actually returns a reference,
Oh.
I think. I'm a little hazy on the details. I've never used it. So I've used this for most of my C++ career.
I'm pretty confused at what all is going on there. Sorry.
That's okay. So
So the vector is a class, right?
right. So this has to deal with with the C++ concept of containers. Let me just put a new slide in here, and I'll go find that slide so I can draw. Whoa, that was too fast. Okay, there's my slide. Okay, so the C++. What the? Go back. Okay. The C++ standard library consists mainly of, well, not mainly, but a large portion of it is the container classes and the iterator classes. So the container classes, this is your vector, your list, your queue, your map, your DQ. Anyway, there's a bunch. Set. Okay, the point of these is these hold other things, hence container classes. So a list is an implementation of a linked list. A map is an implementation of a hash table. A set, well, is a set. A vector is a dynamic array. Okay. And then they tried to make a unified interface to all of these. And they did that through the iterator classes here. So each container has its own set of iterators. And their job is to navigate through the containers. Does that make sense? You follow me so far?
A little bit.
Okay, so their job is to navigate through these in a uniform fashion. So, have you ever tried to write your own linked list?
No.
No. It's painful, okay, to write your own linked list. I got a second on that. It's painful. So, the hardest part of using a linked list is navigating through it. And so the iterator class simplifies that for us. So if I had a list A here, and I want to add stuff to it, well, I can use the pushback method, or I can use the insert method, and so we add some stuff to our list. Okay? And then if we want to loop through everything that's contained in the list, then we can use the iterator. And the way we do that is by saying a.begin. And what this does is it returns an iterator that points to the beginning of the list. There's another iterator that points to the end of the list. Okay? And these iterators are supposed to act like pointers. So you can dereference them, which gives you the value that it's pointing to. You can add them, which navigates to the next thing in the collection. There's a minus minus. Some even support plus equals 2 or 3. I know the vector one does. And so on. And so that way you have a nice syntax for looping through any container, and it all looks the same. Standard vector is special in that a standard vector, all of the elements are contiguous in memory. That is not guaranteed for any of these. Only standard vector is the only one that is guaranteed to be contiguous in memory. And so its iterator actually just happens to be a pointer, because compilers are really good with plain pointers. The other ones, the iterators, are actually classes. So does that make sense?
You're like speaking a different language. I'll have to talk to you about it later.
Okay, well, hopefully I help someone.
I thought I knew C++.
Well, you know C++. What you don't know is the standard library. There's a difference. Ooh, that's funny.
There's a lot of standard library.
And the standard library is ginormous, yes. Anyway, so the point is, use the iterators. They're there for a reason. The compilers like them. Use the iterators if you can. Okay. So anyway, that's the end of that. It took way longer than I was expecting, but that's okay. No, it's fine, Robbie. You're fine. All right, anything else? I will be posting the next project soon. We're actually going to get started on some fun stuff, I promise. We're going to be writing a numerical method to solve the heat equation on a 2D plate. So, and then we can start getting into the parallel stuff and all that other fun stuff. So, anyway, I should stop this.